So here I'm going to introduce the equivalent circuit concept, some ideas regarding that equivalent circuit concept of three-phase induction motor, because this is useful in understanding the power flow in the circuit, the induction motor. And before going into that, I will just go through some important points which are required when we analyze the induction motor performance. Now, the induction motor, as you know, is actually working on the principle of production of a revolving magnetic field. When you apply a balanced three-phase supply to a three-phase winding that is there in the stator of the induction motor, and each of this winding is separated by 120 degrees in geometrical space, and when you apply a three-phase balanced supply, what you get is a revolving field. Now, the revolving field causes an induction of EMF in the rotor windings or rotor conductors, and this EMF will circulate a current if it is shorted. If the ends of the windings or the conductors are shorted, there will be a circulation of current, and this current will interact with the field, and that will create a torque, and that will actually rotate the rotor. Now, as per Lenz's law, we understand that when there is a flux change, the effect will be the eventual effect will be to nullify it. So in that process, what happens is that the rotor tries to attain the speed of the magnetic field, which is actually the real cause of production of EMF in the rotor conductors. In that process, it tries to attain the speed of magnetic field, which is called the synchronous speed. So we refer to as synchronous speed, ns, usually given in PMs, so iterations per minute. And there is this speed. It tries to attain the speed, but it is not able to do that, because if you do it, an EMF induced will become zero, and slowly the torque will not be there. So if there is some losses or frictional things are there, that will retard the machine or the rotor, and it will actually settle down to a speed usually denoted as N PM. It will settle down for a speed which is subsynchronous or lesser than the synchronous speed. So in ideal case, if you are taking, if there are no losses, it will run at this synchronous speed. And in the practical case, there is some loss, frictional or some mechanical loss, viscous frictional and bearings friction. All these contribute to those mechanical frictional losses. So that will retard the speed, and it is a subsynchronous, which is lesser, it will closer to the synchronous speed. So this is how the motor starts to run and runs at that condition. Now, as you load the machine, but depending upon the torque requirement, the speed and will change, and that will actually cause so many changes in the circuit. We will analyze the circuit and see how the induction motor power flow is happening at given slip. Now, there comes another term called slip speed, that is given by ns minus n. It is called the slip speed, and there is something that is called slip speed. Usually, there is some quantity called slip, and this slip is given by ns minus n by ns. So the slip speed referred to the synchronous speed. This is called S, and if it is percentage slip, you multiply this with 100. So this is how the slip plan goes. So just understand this is the thing. And one more thing, the rotor rotates at the speed say n, and the rolling speed is ns. Now the induction of EMF is due to the relative speed. So the frequency at which this induction field is revolving is ns. Now when the motor starts to rotate, there is a relative speed, and that affects the induction of the frequency of induced EMF in the rotor when it is rotating. So for example, if it is standstill, you can say that it is same frequency, because it is seeing that the speed, and the speed at which the field is rotating is ns. Now when it starts to rotate, at standstill, this is the frequency, how that flux is f. And when it changes to the speed, the speed is 120 f by p. So this p is the number of poles for which it is formed. This quantity also may be noted. We are not going deep into those definitions, but just understand what can be f by p. Now this is ns. Now when it sees a difference ns minus n, then obviously there is some it will have another frequency f dash. So now the same number of poles, the rotor and stator, they want for the same number of poles. So then this f dash is again that is 120 ns minus 20 f, sorry, f by p is 120. So f dash is p into ns minus n divided by 120 f. Or f here you can put in another way. F is p ns by 120. So p is the number of poles, the same. Now in this case, when f dash, that is when there is some relative speed, this f dash is p ns minus n by 120 f. You will see that this, what is the relationship between ns and so p is equal to s. So s is equal to ns minus n divided by what we call ns. So s ns is equal to ns minus n. So thus that you can substitute here, and finally what you get is f dash, the new frequency of the rotation when induced EMF in the rotor is f dash, the frequency of induced EMF in rotor is equal to s times this is the slip. It is not in percentage, it is in actual value, that is ns minus n by ns. So sf, so f dash is equal to s. Just please keep that in memory. So now this is the situation we have seen the background data that is required, and we will now approach the equivalence circuit. So here you will see we are drawing a per phase equivalence circuit always. So all the quantities, all the values are referred with respect to a phase. So per phase equivalence circuit, and then we can, those concepts which were developed in the single phase equivalent circuit, single phase transformer equivalent circuit can be used here. And the idea is if you draw a three-phase equivalent circuit, it is very difficult to interpret and to get some meaningful information. So if you construct a single phase equivalent circuit, since everything is balanced, every winding supply of those things are balanced in the case of a three-phase induction motor, if you draw it for a single phase, you can construct, or you can imagine, you can derive the quantities, three-phase quantities from that single phase circuit, because everything is balanced. So that is the idea. So we will be drawing a per phase equivalent circuit. Now, how can we draw that? So we are just considering the per phase equivalent circuit, and we are denoting the, say, RS, the stator resistance per phase, JXLS, the leakage reactance of the stator, that is XLS, and R naught, the iron loss component. It is I naught. It is derived. It is split up into two parts: one for meeting the iron loss and one for magnetizing IM or IMU, whatever. Now this, say, E1, and this is, say, E2 for the time being. Now it is open circuited. That means the motor is in the initial state, or it is even if you provide a supply, it won't rotate. That is the situation. Now in this case, if you compare it with the transformer, you can say that it is almost same. Everything, the windings, resistance, leakage reactance, the induction of EMFs, and primary and secondary. Here it is stator and rotor. Now this notation I used in a similar way. Just see that there will be, so let us hold it. Okay. Let us there will be some rearrangement and see another notation. And see that it is open circuit, it won't rotate. So it is, this case, it is it is equivalent to a transformer. Remember that for squirrel cage you cannot do it, because you cannot open the transformer motor windings. It is a solidly connected thing, you cannot do it. But in the case of a slip ring induction motor, where it is the rotor is having a winding, phase winding, phase one, or windings are also there in the rotor. This is possible. You can open circuit it and see that. But just see for the analysis purpose. This there. Now, when you close it, there will be some current I2, and obviously, suppose it is rotating with a slip S, some speed, and suppose it rotates with S, and this will be S times E2, where E2 is the thing, where this what do you call it? The induced EMF when it is stationary, rotor is stationary. So S, it becomes S. How that comes is, you can see the induced EMF V per phase. So it is 4.445. So N, some conductors N2. Now when you change this F to SF, it becomes S times whatever quantity it was previously. So let us call some E dash. So E dash comes, so that is what? S times E2. So it changes to that value. Okay, so that is not right. So this is the equivalence factor, and this is the similarity between transformer and induction motor. And induction motor is often referred to as transformer with rotating secondary. Rotating secondary, because the rotor it will may revolve. If it is shorter, it will carry a current, it will interact, and it will rotate. Now see here, there is this what you call the air gap. There is some reluctance because of air gap in the case of an induction motor. So that will bring some issue into the circuit, where you can see that this magnetizing branch reactance is significant, or it will carry a significant amount of current. You cannot neglect that. So your initial approximate equivalent circuit of transformer actually consider. You can shift this magnetizing branch to the left and simplify it. You cannot do it in the case of induction motor because of this heavy, relatively high amount of magnetizing current that is required in the case of transformer because of the air gap presence between the stator and the rotor. There, in the case of here, there will be some part will be iron and some part will be air. So the magnetic circuit involves an air gap. So that will create this extra. So this, suppose this is stator and rotor. So this, there is some gap that will demand more magnetizing current. So you cannot neglect this part. That is, you cannot, as a wish, can take care of. You cannot do like that. But you have to see it in actual terms and see. Now, here it is, the frequency is F, and when it is running at with a slip S, the induced EMF is this, and the frequency is like this. This SF, if it is F dash is S times. So the actual inductance or the leakage reactance will change to SX2 because L omega is that reactance. So L remaining the same when omega changes. Omega is 2 pi F. 2 pi F dash it is. So it changes to SX2. So observe. So I will draw the rotor circuit separately to see that change and appreciate that. I have, when it is running, I have this situation, it is shorter. So you have SC2 here induced, plus R2 and JSX2. Okay, so here there is one problem. In the case of transformer, you can have this, and so in the case of transformer, such a situation, when you transfer this to X2, when you transfer, you just ignore and take out this and do some the transformation manipulation to fluctuate value resistance. You can make it R2 dash, X2 dash, R2 by K square. So in the case of transformer, it is possible because here the frequency in the primary and secondary part they are same. Even if it is separated, the frequency is same. So there is no technical problem when you connect both of them. Now, as a single circuit you can do that. But in the case of this induction motor, that is not possible because the frequency here is different from the other. You cannot do that. So what you do is some manipulation. That is, you have this current I2 which is going through that circuit, rotor circuit, shorted current, which is equal to this. These are all quantities are per phase. So just understand. So S E2 by R2 plus J S X2. This is the current. This is how you get the current phasor. Now do some manipulation like this. Divide throughout by S, and you will get. See, so E2 by R2 by S Jx2. These are resistance of the winding R2, and X2 is the leakage reactance of the rotor. R2 is the resistance of the rotor per phase. X2 is the leakage reactance per phase. E2 is the per phase induced EMF at standstill. So this is the change that we do. See, the same situation. This I2 you obtain in the same way. But here, this I2 you can definitely say that this with the frequency S. Other thing, I mean, if that is just then, because you can certainly say that it is X2, that is this omega is 2 pi f, not f dash, and E2, it is not SC2, it is E2 itself, the standstill voltage, for the same frequency. So this I2 is obviously in the same thing, and your resistance, it is manipulated, some value which you manipulate to get a convenient way of representation. So you can change this circuit, this rotor circuit, to a new form to make it ready to get connected to the stator. That is this in a similar way that we do in the case of reference, equivalent circuit referred to one side of the transformer. So here what you do is you have your SE2 becomes E2, and this becomes R2 by S, and this is JX2, the leakage reactance. So this carries the current I2, which is not the same frequency, and here see this is changed. R2 by S is changed without causing any casualty in our analysis. So now at this stage, just I am just trying to relate it to the power. What is happening? So eventually the power is transferred to the load from the rotor. The rotor shaft is there, so mechanically coupled to some load. So it is transferred from rotor. So in this circuit, everything is there. That is, this power, whatever power that is transferred, should come from this fashion, from this electrical circuit. So everything, this induced EMF is there, the current is there. So if you analyze, so eventually, as in transformer, this output power should be there to represent these things. How can you do that? Now you know that when I2 is there, copper loss is I2 square into R, right? So the copper loss is I2 square into R. These things are, everything I refer to is per phase. So this is also per phase. So current into the rotor resistance per phase. Now this is hidden here. How? Because we see only R2 by S here. Doesn't mean that the rotor copper losses are not I2 square R2. Instead, it is something which is comprising of rotor copper loss plus something. Now, and if you split this up, say R2, J, you get something like this. Right. R2 jx2 R2 by S minus R2. So this in this way you can see that copper loss is there, and rest of the thing represents something else. So that something else is nothing but the what do you call the mechanical equivalent, electrical equivalent of mechanical load that is appearing on the shaft. That includes everything, the loss, the load torque, everything. I mean, load, everything is comprised of this. So you can say that this is equal to R2 into 1 by S minus 1. Or is equal to R2 into 1 minus S by S. Okay, so this is the this is electrical copper loss, and this resistance is equivalent to mechanical the power output. So you can say that I2 square R2 into 1 minus S by S, that represents voltage. VA is the power. That way we can get this. That represents the power that is the total mechanical power that is generated. Whereas I2 square R2 is the copper loss. So this is how you calculate the total power output, and you can also find out what is the total power input. So power input should be obviously where this power is expended. That is, one is here and here. The resistance only dissipates power. So in that idea, if you go by that idea, you can see that the total power that is input per phase is equal to loss here plus this mechanical power output. So this sum will give you the total power. So you end up with the total power input per phase is equal to, say, I2 square R2 by S. That's the sum will end with this. So this is the total power input to the rotor, and the rotor uses it to meet different losses and output power. So this is how you find the relationship with the load and the rotor resistance. So rotor resistance is related to load by this relation. This kind. So you can write, I think this is understood. So you can take it out and write down the ratio of how it is related. So you have three quantities, that is P input to the rotor. It is the rotor air gap power that is input, that is so I2 square by R2 by S. Then copper loss in rotor, per phase, everything is in phase quantity, I2 square R2, and total mechanical output, that is I2 square R2 into 1 minus S by S. Remember that this is inclusive of rotation losses also. So you can see that so everything is related like this: 1 by S, 1 minus S by S. If copper loss, say, per phase is given for rotor, so this is relation again. So if you put 1 by S or 1 by S into PC, you get the total input air gap power. and if it is just this u is doing like this, and if you multiply by 1.6 and divide by s, you get the total mechanical power output. And from that, if you know the rotational losses, you minus that loss from this value and you get the mechanical power output. You know the speed of the machine, slip will be given. Then T omega, 2 pi, omega is 2 pi by 60. So T you can easily find out. So that is how you solve different quantities with this, with the aid of this equation. Now, now we have done some manipulations. Again, I will read the original diagram which we saw. This is not and JXM. And this is supposed to carry a very heavy current, this XM, compared to the transformer magnetizing branch. Minus here it is V2 and V1. So this is the situation now. The frequency is changed. The current frequency here is I2. It is changed. Now this is I2 dash. This is I1 and this is I0. The frequency is changed now. It is now ready for this transfer of impedance, as in the case of transformer. So here E2 dash, that is when you transfer this to this side, it becomes equal to E1. So you remove it and you can do like this very simply. You can understand. So this is the diagram, equivalent circuit, of the induction motor referred to as it. Now, when you do it, this manipulation that, so let us say the rotor resistance, say J into 1 minus S by S, J